Welcome back. Where we left off, we were using this formula up here, which should make some intuitive sense to you, and I'll prove it if it doesn't. But we're using this, and it's neat because it involves vectors instead of just pure variables, so there's actually vector variables. But we're using this to figure out, I hit a ball that was 4 feet off the ground with a bat, and I want to see if I can, and I know its initial velocity and its angle, and I want to see if I can clear this fence that's 350 feet away. And we do that, we use this formula, and we work through it to get the position of the ball at any given time, which I think is neat in 2 dimensions. And we could have actually used this in 3 dimensions if, I don't know, if we were in 3 dimensions. So let's go back to where we were. We got to this step, and now we can simplify this. So the position at any given time. I'll write let's say the x position. So what are the terms that involve I, the unit vector I? Well, there's only one right here. Right? So that's what tells us the x position of the ball. So it's 60 square roots of 3 times I. And then what tells us the y position of the ball? Oh, sorry, I got rid of the t. There's a t here. Times time. That's a t. And then what tells us the y position? We'll have this positive 4j. That was its initial position above the ground. And then I have 60tj, and then I have minus 16t squared j. So what we could do is then we write plus, and there's going to have multiple terms in it. So let's group all of the things that are multiplied times the y unit vector. So we say 4 plus 60t minus 16t squared j. And there we have it. We now have the position, the x and the y position of the ball at any given time t. And actually, let's look at this. Let's see if this makes sense. So the x position is just a linear function of time. And does that make sense? Well, sure. It's if we remember the 60 square roots of 3, this was just the x component of the initial velocity, right? That was just this right here. And since there's no other force acting in the x direction or the horizontal direction, we stay at that constant velocity. We don't accelerate or decelerate. So at any given time, the distance that we travel in the x direction is just the time times the velocity. So that makes a lot of sense, and that should make intuitive sense from what we learned when we originally did the 2-dimensional projectile motions without using the unit vector notation. Good enough. So let's look at the y position. So if you look closely, this whole y term here, this whole thing, it looks very similar to our initial equation. And that's because we start 4 feet off the ground. And notice we didn't have a, we didn't have any term like the 4 in the x position because we started at x is equal to 0. Or we just defined that we're starting here where x is equal to 0. Otherwise, we would have a term here for the x position. We start 4 feet off the ground. Our initial y velocity in the y direction is 60, right? Because that was 120 times the sine of 30 degrees. That's this component. That component was 60. So our initial vertical velocity was 60 feet per second upwards. And then our downward acceleration, all affected in the y direction, and you take the 32 divided by 2, and you get the 16. And it's minus because acceleration is acting downwards. So what we have here is a very neat way of knowing at any given time, I could say after exactly 2 seconds, where is the ball? And actually, I could use this. I could draw a cartoon. I could show the path of the ball. Like if my cursor was the ball, I could plug this into a computer program, and then the computer program could just draw the trajectory of the ball. But anyway, let's get back to the problem and let's see if we can solve it. So we want to know, is the ball at least 30 feet in the air, because that's how high the fence was, right? We said it was 30 feet in the air. When it has gone 350 feet in the x direction, when it has gone 350 feet. So how long does it take it to go 350 feet in the x direction? Well, this term right here has to be 350 feet. So let's solve for time. 60 square roots of 3 times time has to be equal to 350. Or that, so let me get the calculator out. Or that time, I'm running out of space, time has to equal 350 over 60 square roots of 3. So let's see what we can do. Get the calculator. So 3 square root times 60 equals, okay, and now that's in the denominator, so let me invert it, times 350. Okay, so let's say 3.37 seconds. 3.37 seconds equals 3.37 seconds. So this ball's moving fast. It went 350 feet in only 3.37 seconds. Oh, I guess that makes sense. I mean, when I look at a baseball game, the ball's not in the air that long. So at 3.37 seconds, how high is the ball? Well, we can figure that out by using the y component of our position vector. So let's do it. Okay. So let me clear this. So it's 4. Let me do it. Well, let me do each of the terms separately. So let me do this hard term first. 16. I shouldn't have deleted that. 3.37. Oh, this doesn't have a squared button on it, does it? No. So I'm going to have to do it times 3.37 is equal to 11.53, and then times 16 times 16 equals 181.7. So this term here, let me do a different color. This is equal to 181.7. What's 60? 60 times 3.37, remember that was the time, is equal to 202. This is equal to 202, and then you have the 4. So see, you have the 202.2, and then you add the 4, and then we're going to subtract this number, right, because it was minus 16c squared. And you say minus 191.7 equals 14.5 feet. So at 3.37 seconds, the y position, so we can even write it like this. Let me see, I'm running out of space. But we could say the position at I'll just write it as 3 seconds, is equal to 350 I, right? Its x position is 350. And what's its y position? Plus, well, we just figured it out. We substituted 3.3 seconds into the y piece, plus 14.5 j. Right? This is its y component. So it's going to be 350 feet, and it's going to be at 14.5 feet in the air. So the ball would have flown like this, and it's only 14.5 feet in the air, so it's not high enough to clear the wall. So it's going to hit the wall and bounce off, and that's out of the scope of this project to happen to what happens after it bounces off. But we know it's not going to clear the wall. So hopefully I haven't confused you too much. I know I ran out of space, and this looks a little bit hairy, but I think you'll see that what's neat about the vectors is that now I can do these problems in an arbitrary number of dimensions without having to kind of separately draw the x and the y positions, x and y vectors. And what's especially neat is I can get a function, a vector function, that tells me the position of the ball at any given moment in time. And that's relatively new. I don't think we actually did that in any of the other projectile motion problems. So that's it for now, and I will do a couple more of these problems very soon. See you soon.